I'm Jim Vajda, Chief Wireless Officer here at 7Signal. I'm a CWNE and a couple other things. And, today's topic is about OFDMA and, how we can get more of it, what some expectations have been and maybe should be for it. And I want to start by first, let's see, there we go. I want to start by first just talking about, the problem that OFDMA solves. One of the things that has been an ongoing problem with Wi-Fi in its whole history has been that as each new PHY is released, each new generation of Wi-Fi, 802.11b, G, and AC, we've gotten faster data rates, which has made those, marketing numbers on the sides of the AP boxes really high. We went from 1 megabit per second now up into tens of gigabits per second, theoretically, over the air with data rates. And when we're doing that, what we're actually doing is optimizing the throughput that's possible to deliver to one client from an AP. Well, but what hasn't happened is we haven't really actually been able to increase the amount of packets that we can deliver very substantially in a limited amount of airtime. So just to kind of make that point here, we're looking at an example from actually a friend of 7Signal, Yermund, and I'll put the link to his airtime calculator where you can play with this and generate your own examples in the chat. But this shows the amount of airtime it takes to send 2 frames, right? They both have a 300 byte payload, which is pretty common for Wi-Fi packets. 2 spatial streams, normal guard interval, 20 megahertz channel, and 12 megabit minimum basic rate. So, pretty typical conditions here. And they're just sending 1 packet, so no RTS, CTS protection necessary. And at MCS 0, which is really, the slowest most clients will go, the transmitting that frame takes 247 microseconds. But if we were at MCS 9, the fastest speed available to an 802.11ac device, it still requires 227 microseconds. We've only shaved off 20 microseconds. So how is that? Why is that? Well, the issue is with the channel access protocol and all the backwards compatibility and legacy baggage that Wi-Fi has accumulated over the years. If we look at the first 2 fields here, and why is my screen keeps going black? The diffs in the CW, it's actually probably an AIFS. That's just dead air where we're winning channel access. Then we've got the legacy preamble, and then the PHY header, and then the AMPDU. And the AMPDU is actually the only part of this whole process that benefits from that higher data rate. That's the part that actually shrinks a little bit in the airtime consumption when we go to MCS 9. So the point I want to make is the actual number of packets that we can put through the air hasn't really changed significantly throughout the 20 plus year history of Wi-Fi. And this isn't so much of a problem with consumer stuff or low density networks, because again, we're talking about microseconds here, right? So big deal if it's a little bit wasteful in airtime. But it is a problem with very high density, very busy clients with a lot of small packets to deliver. And a lot, often, studies have been done that have shown that most, the large majority of the packets that are sent back and forth in Wi-Fi networks are small packets. You can think of, DNS requests, extremely small, ARP traffic, DHCP. Even application traffic like web browsing and email, messaging, notifications, voice, it's all very small packets. Sometimes video streams even use somewhat small packets, right? If there's a lot of compression. So we haven't really improved our handling of those very, very small packets that much. And that's what OFDMA helps with. So here we've got a graph that shows OFDM, which is how everything has been modulated since 802.11a. How that compares to OFDMA, which is new for 802.11ax. With OFDM, right, one user, an AP or client, transmits at a time, and owns that whole channel. Nobody else can use it while they're using it, even if they're just sending a really small packet, like an ARP packet. They're the only user, and they use the whole channel, even if it's an 80 megahertz channel. They use it all for that teeny tiny packet. And we go through this whole channel access procedure again to get that packet across. So it's wasteful from an efficiency perspective. And that's where OFDMA comes in. This is really what made, puts what the main feature behind naming 802.11ax high efficiency. It's the high efficiency amendment to 802.11. And OFDMA is the primary means that we increase efficiency. So what we can do with OFDMA is, instead of sharing, or instead of allowing a single user to dominate the whole channel, one user at a time, we can divide up the channel, right? If we're just sending an ARP packet, we don't need 80 megahertz. And if there's a bunch of clients that all want to send ARP packets, well, let's let them all do it all at the same time and just subdivide that channel. And so that subdivision creates these resource units that are assigned to each user. So this is really a huge change. OFDMA is pretty amazing. It's very, it's also a very proven technology. This is, and also, a couple decades old. WiMAX used it, LTE, 5G. It's really at the bedrock of those cellular technologies, and it's how they're able to, have thousands of phones connected to a single tower and orchestrate all the traffic with the very limited spectrum they have access to. So it makes sense for us to adopt this in Wi-Fi and help solve that problem of spectrum inefficiency. And the way that, one of the other things that's unique here is that OFDMA is scheduled channel access. So with OFDM, we use EDCA, we use that distributed random access channel access procedure, where each station, the APs and the clients, use the same contention rules, and emerging from that is this order where the channel is shared without it being centrally managed. With OFDMA, now it's centrally managed. The access point is scheduling all of this traffic. It's telling the clients when they transmit, into what resource units they transmit, and when it's going to transmit simultaneous downlink frames to clients as well, and how that's going to go. It's all under the control of the AP. And it has to, the scheduler is the software the AP uses to make those decisions. And it has to take into account the size of its buffer, what it knows about client buffers, channel conditions, access categories of frames, and a lot more. One of the other benefits, though, of OFDMA is that we're doing that channel access protocol less often. If clients are transmitting simultaneously during one period of OFDMA, then the AP has to win channel access for that to happen once, instead of each of those clients having to win channel access individually. So there was a lot of excitement about OFDMA when it came along, but there's a lot of complexity involved in it too. And one of the ways to think about it is the AP has to answer this eternal question that comes to us from Shakespeare. He says, to schedule or not to schedule, that is the question. So in 802.11ax, we still have all the legacy channel access procedures available to us. And we can still transmit to one, we can still use EDCA for distributed channel access, and one client or AP can transmit at a time. And so we call that single user mode, right? So OFDMA is multi-user mode, or when scheduling occurs, and single user mode is when we're just going back to the distributed random access where one station wins the channel at a time. So the first question that the AP has to answer before OFDMA ever even happens is, should I schedule the channel access or not? And actually, should I use OFDMA or multi-user MIMO for that? So a lot of times, and the answer is actually, it's maybe not the best time to schedule channel access right now. And actually, those answers are pretty unintuitive. So, I think this is one of the reasons why there was a little bit of a letdown when we started looking at some of the 802.11ax products out there, and didn't see a lot of OFDMA. I think the marketing was out ahead of what was actually realistic in terms of the frequency at which we'd see OFDMA, because a lot of times it just doesn't make sense to use it. And so, some of the reasons that we don't see OFDMA very often today, first is we're using spectrum that's shared with legacy clients. A access point operating in 2.45 gigahertz probably has a lot of clients that are 802.11n or AC connected to it. And they have to compete, those access points have to compete with those clients for channel access. And when the AP wins channel access, that's when scheduling and OFDMA can occur. So if it's competing with clients on an equal footing, then the possibility of scheduled access is lower. Of course, legacy clients can't participate in scheduled access. So when that decision-making happens, the AP has to factor in, well, maybe only 10% of my associated clients are 11AX. So if I'm going to schedule, I can only do it for 3 or 4 of them. Well, that's just not even worth it, because I'm already in single user mode with these other clients. So forget it for now. Related to that, one of the triggers for scheduled access is having a lot of buffered data. If only a single frame is, a single packet is getting to that AP radio, then the question of should we schedule anything is kind of moot. Just empty that buffer and transmit that frame in single user mode and get on with it. So we need to have buffered data, building up at the AP for downlink and building up at clients for uplink OFDMA. And of course, only 11AX clients, only the traffic to and from them is going to be considered when it's buffered for scheduling. Wi-Fi is really fast in single user mode. So if we don't have a lot of connected clients, like I talked about at the beginning, just a couple clients or just one client, we can deliver a huge amount of throughput to them. And there's no need to get fancy with scheduling. And then, single user mode has had some efficiency gains that we'll talk about in a couple minutes here, that thanks to frame aggregation, that actually make it pretty efficient from that perspective when we don't have a lot of connected clients. The other, another reason why we've seen less OFDMA is if we have a really good Wi-Fi design, if we followed a lot of the best practices for Wi-Fi design, one of the outcomes from that is that we've actually optimized channel access. If you think about, removing and limiting co-channel interference, well, that means there's fewer clients and APs on the channel, and the likelihood that when they need channel access, they'll get it is higher, which means the buffers are emptier, and there's less need for for scheduled OFDMA. You actually need some congestion for OFDMA to make sense, and that's not as often a property of well-designed networks. And then maybe, pessimistically, maybe the scheduling software and the protocol aren't fully baked. Maybe what was released on day one with 802.11ax products, wasn't ready for prime time, and the scheduling, it's taken time, and it needs even more time for the chipset vendors to improve their scheduling algorithms, and perhaps it's hard to say, right? That's a black box. The scheduling software is actually proprietary, so the standard, the 802.11 standard, doesn't dictate how a scheduler makes decisions. It just says here are the tools a scheduler can use. So I want to talk through an example, and actually this is where we'll bring up that poll, Heather, if you don't mind. But I want to just get a pulse from the audience on this question of scheduling. So hopefully everybody can see the trivia question, but the question is, what mode of operation will consume the least airtime in this scenario? So less airtime means more efficient. So say we have a 4 spatial stream 11AX AP, and it has 8 connected clients, and it needs to send each of them 80 kilobytes. So that's a lot of buffered data. That's over half a megabyte just sitting in its buffer. It needs to clear. And they're all AX, right? And they're all 2 spatial streams. They have a good connection, good SNR. And then the AP is using a 20 megahertz channel width. So what should the AP do? What's going to use the least amount of airtime? Is it OFDMA? Is it multi-user MIMO? Or is it just unscheduled single user transmissions?
Starting to roll in now. I was getting a little nervous at first, but I think this one got everyone engaged.
Yeah, I think people wanted to hear if I was going to give some more clues.
This is a good one. All right, I'm gonna close this bad boy out in 3, 2, 1.
So there we, Yep. So there we have it. The majority opinion was OFDMA would be the best choice. That's what my gut told me too. Of course it's OFDMA. We've got a lot of buffered traffic. It's pure 802.11ax. And there's 8 clients. That's 8 active clients is actually a fairly high number of active clients to be actually transmitting or needing to receive at the same microsecond in time. Well, I put this question up because it's interesting, because the real answer is actually single user mode, right? So it's the least popular answer, and most of us would say this is exactly the scenario that we got OFDMA for, but we would be wrong. We would consume less airtime in the scenario where the AP used single user mode. So that example is actually from this book I'm showing here, Wi-Fi 6 Protocol and Network by the 2 gentlemen there. And if you really want to see the math and details and other examples, that is a really good read that helps illuminate when scheduling does and doesn't make sense and why that is. So interesting book. I'll actually drop this link to the book in the chat as well. Okay, so we all got that wrong, including me, but that's no surprise because it's actually a very hard thing to know. One of the things I mentioned though is in single user mode, we do have some efficiencies built in, like frame aggregation, which we got really serious about in 802.11ac. Every data frame sent in single user mode is actually sent in this aggregated frame format, AMPDU. And if there's a client that has a lot of needs a lot of data or needs to send a lot of data, we can use this aggregation method so that we only go through the channel access procedure once. In this case, this is downlink from the AP. The AP wins channel access, and then it gets a TX op, which can be quite long, over a millisecond in some cases, and it just sends frames one after another, aggregated with nothing in between on the downlink until it's either used up the whole the maximum amount of time it can, or it's emptied its buffer to the client. So that's one reason why single user mode is a good choice in many cases. And I'll talk about how we can increase scheduling going forward, because I do think this is going to happen. I think we will see more OFDMA, and I think the most obvious place that we will be 6 gigahertz. 6 gigahertz benefits from having no legacy PHYs, no previous generations of Wi-Fi, so no other clients, legacy clients competing to win channel access with the AP. And so the AP can dominate channel access in 6 gigahertz. I'll explain how that can happen, since all the clients it's dealing with are 11AX. Also, when the AP is making that decision about scheduling, all the traffic that it's looking at now in 6 gigahertz can be subject to scheduling. So it's not just a fraction of the traffic it's dealing with, but all the traffic in its buffer and in the client's buffers can be scheduled. We'll also use wider channels. 80 megahertz is going to be the default channel width and deployed channel width in many enterprise networks. And that has benefits as well. That means more simultaneous clients can be scheduled at once. And eventually we'll even be able to go up to 320 megahertz channel widths with 802.11be. That's another story. So even in the legacy bands, the increased deployment of 11AX clients means, the greater proportion of 11AX means, the scheduler has more traffic that it can consider when it's deciding to schedule or not and use OFDMA. And then, the multi-user EDCA parameters and being able to tune those, which would be really wonderful, can affect how often scheduling occurs. And I'll get into the details of that. But I mentioned that wider channels allow more users to be scheduled at once. If we're, and I think this, may have played into that scenario. You may have noticed it was 20 megahertz channel width, which is a common channel width in 2.4 and 5 gigahertz to use in the enterprise. But that limits, how much spectrum is available for OFDMA and the number of users, although we could still do 9 at a time in a 20 megahertz channel. But in 6 gigahertz, where we'll have, again, 80 megahertz channel widths predominantly, now the scheduler can schedule 37, up to 37 clients at a time. So it's, most of the time, all the clients can be scheduled in the same period of OFDMA, if there's less than 37. And if there are, say half that number, well, they can get twice, RUs that are twice the size and still use all the spectrum really well. So that's going to impact the scheduler's decision making. So multi-user EDCA, we don't need to get into all the details of what I'm showing on this slide, but this is just a look at the uplink OFDMA channel access procedure, and I did describe the details of this in my WLPC talk. But one of the things that happens with uplink OFDMA that's unique to 802.11ax clients is that after they're scheduled, once they've been scheduled once for uplink OFDMA, now they have to abide by a different set of EDCA parameters. We've got those WMM EDCA parameters that tell us the size of the contention window and the interframe spacing for the different QoS access categories. Well, once a client's been scheduled, now it's actually using a different set of multi-user EDCA parameters. And here's an example of one showing that these EDCA parameters are, require a longer contention window in AIFS than the normal ones, the WMM parameters. Now, only 11AX clients will use these, but what this is doing is saying, well, yeah, you can still contend for the channel and win channel access as a client, but you're going to take, your statistical likelihood of winning channel access is now reduced, but the access points likelihood of winning channel access has not been reduced. So this is a way of getting clients to sort of get forced into scheduled channel access, because the AP should be winning channel access a lot more often with enough clients falling under these rules. And then OFDMA can just kind of cascade on and on and on as the scheduler, addresses the, emptying the buffers of the connected clients. That's the hope. So this is an interesting feature, and it's got a timer. So if the client isn't scheduled and before that timer expires, then it goes back to the normal WMM parameters. So if the scheduler is neglecting a client, it does have an out here. It can also use a operating mode indication frame to just say, count me out from uplink scheduling. But I don't know if that's always if that would be a wise thing to do. The other capability of the multi-user EDCA parameter set is we can actually set, if we set the AIFSN to 0, that tells clients that for that access category, they're just barred from contending for the channel using the single user channel access procedure until that timer expires. They can only be scheduled for that access category until that timer expires. And every time they get scheduled, the timer resets. So if you think about this, think about 6 gigahertz where we've got a pure 11AX environment. We're going to use wider channels, which gives the scheduler more flexibility. We can get aggressive with these multi-user EDCA parameters. And if a Wi-Fi network has very high density of clients and they're very busy, then I think scheduled access is going to be quite common in those scenarios. One thing I'll note, though, as far as I'm aware, none of the AP vendors let us change these multi-user EDCA parameters. They're just what they are out of the box, unlike the WMM parameters where we can often tune those for our needs. So it'd be wonderful if any AP vendors are listening out there to give us the tools to, especially like the AIFSN. We'd love to be able to toggle that to 0 or not, depending on the design goals of the network. Okay, I think that about wraps it up, Heather, and maybe we have some time for some Q&A. If you've got some good questions.
Yes, indeed. All right, let's start at the top. So Rick asks, can you talk about Wireshark? How Wireshark can be used to be able to see into the individual RU streams? We need to be able to verify OFDMA is working correctly.
Yeah, good question, Rick. So Wireshark, of course, can read anything that you give it. It can see, it'll decode whatever you see. The challenge is on the capturing hardware. Can we actually capture a full OFDMA transmission and see each of the RUs? And the answer is no, not with the hardware we have today. There might be specialized lab equipment that can do that, but with a laptop or a typical capturing device, a WLAN Pi, you sort of can set it to follow a single client and capture its RUs that are assigned to it, but you can't see everything else. Now, what you can do though is look at the management and control traffic that surrounds OFDMA, and you'll also can see the preamble for downlink OFDMA in Wireshark. You just get these just sort of packetless preambles that are multi-user, where the multi-user bit is set, and you can see what's going on there. And then in the uplink direction, you can look at those trigger frames, which explain all the resource unit allocation and the other characteristics, the MCS and target transmit power for the clients. So you know what clients are going to be scheduled But it's a big challenge to be able to actually capture that OFDMA traffic. So good question.
Awesome. All right. Anonymous asks, will OFDMA only apply to an AX client connecting to an AX AP, or does it benefit AC clients as well?
Good question, and no reason to be anonymous. There are no bad questions. It only applies to AX. Only 11 AX clients and APs can participate in OFDMA. It might benefit 11 AC clients in that when airtime is reclaimed from increasing efficiency, then the legacy clients benefit from that, but they don't actually participate in OFDMA.
Awesome. All right, we've got a couple more here. Oh, and I say that and another rolls in. Awesome. Keep them coming. All right, so Rick is back again. He says, our testing has not shown significant improvement over 11AC for 4 concurrent STA, all sending smaller frames. Wondering what others are seeing.
Yeah, that's interesting, Rick. And I'd love if you have a blog post or anything like that to share, because there's been a lot of tests like that have shown, for instance, throughput isn't significantly, actually is actually sometimes goes down when OFDMA is occurring, and wondering, what's going on. It's definitely something the scheduler has to take into account. It's not always the best choice. For concurrent stations with smaller frames, that's a situation where maybe channel width comes into play, or maybe, single user aggregated AMPDU works just fine, and there's no reason to do anything else. Mm-hmm. But one of the things that OFDMA might still provide, even if it's not a throughput increase, a net throughput increase, is that if there's voice traffic, it may allow that traffic to be transmitted across the medium with less latency, because the scheduler can take that into account.
Awesome. All right. Olivier, let's take your question. Have you changed your design approach in 5 gigahertz with the introduction of OFDMA and 802.11ax, or do you still design for 802.11ac?
Yeah, good question. I think no. I think that you don't need to change your design approach in 5 gigahertz. I think you don't need to change the targets you need for cell edge RSSI. You still want to reduce CCI as much as possible, and like we discussed in the legacy bands, there's still primarily single user traffic going on and very little OFDMA. So I would design with that in mind.
Awesome. Got a few more here. So Fang asks, is there a known test report that evaluated OFDMA throughput performance? Off the top of your head, Jim.
Can't quote something off the top of my head, but I would imagine there's some good IEEE research papers out there that have that spelled out.
Yeah, maybe we'll get back to you on that one. Do a little research. Ray Montoya asked, can you explain the difference in frame aggregation methods?
Yeah, AMSDU versus AMPDU. AMPDU is sort of the surviving frame aggregation method. And what it does is it takes this, basically the whole frame, the data payload, and the MAC headers for every frame, and it aggregates that. So every frame within the AMPDU has its own MAC headers. AMSDU was introduced in 802.11n, and we don't see it as much anymore because it aggregated all the frames for within a single set of MAC headers. And so that meant that you had to have the same, it meant that you had to retransmit the whole aggregated frame if any of those were not received because the hashes and so forth were across the whole frame. So AMPDU is the common one you'll see out there now.
Awesome. All right, and then we've got Jose in kind of in the chat, and then also in the Q&A panel asking a little bit more. So with OFDMA, will it be possible to increase maximum number of devices per AP?
That's a good question. If in a pure 802.11ax environment, I think the answer is yes. But it'd be something that would be interesting to test. And also, of course, very much depends on the applications in use. Mm-hmm. But certainly networks like very high density networks, stadiums and arenas that might have over 100 clients on a single AP radio are hoping that it will benefit them for sure.
Awesome. All right, let's take one more. And I'm not sure if I'm going to pronounce your first name right, so I apologize. Peru Kumar. So it's a two-parter. So part one, can all RUs be scheduled to one 11AX client? Part two is for 2x2 80 megahertz client. When OFDM and OFDMA is used, the max T-put input, maybe, I don't know what that means, will be the same, question mark?
Yeah, I'm reading it. Yeah, so the first question is, yes, actually the answer is yes. You can schedule basically a single resource unit for one client. And why would you do that? Well, why would the scheduler do that? One scenario would be you've got a pure 11AX BSS and all the clients have been scheduled. And so in order to continue scheduling and not have to wait for that client to win channel access in the uplink direction when it has a big buffer it wants to empty, and it's going to take a while for it to win channel access, or maybe it's even barred from winning channel access from those multi-user EDCA parameters. Just schedule it to use the full channel if it's the only one that's got traffic to transmit. In some cases that makes sense. Yes, T-put equals throughput. Yeah. So the other
I kind of figured that at like my brain added it up after I had read T-put. I was like, you kids and your hip lingo.
Yes. So for a client in that scenario, will the max throughput be the same between OFDM and OFDMA? Yeah, I think it should be pretty comparable. I mean, we're still using all the subcarriers. I mean, there might be some differences in the AMPDU length and single user mode versus what can happen during OFDMA, but I would imagine them to be pretty comparable.